In this video, we're getting into an alpha particle, in other words, a helium nucleus, and we're looking at forces and energies that are going on within the nucleus. And we start by saying the charge radius of the alpha particle is given by 1.68 femtometers, and there's just a quick reminder, femto means 10 to the negative 15. And then we're told the proton-to-proton separation should be that same value of 1.68 femtometers. So I drew an alpha particle here just to illustrate why that's true. If I look at the center-to-center separation of these two protons, that's equal to 2 proton radii, and the diameter of this entire alpha particle is equal to 4 proton radii. In other words, the separation distance is half the diameter of this alpha particle, and that makes it equal to 1 radius of the alpha particle. So in part A, we're going to look at the electrostatic force between those protons just to get a sense for how strongly they're repelling each other. In part B, we look at the electrostatic potential energy between those protons. In part C, we're going to look at the total binding energy for the alpha particle, and that includes both the Coulomb force and the strong nuclear force. And in part D, we're going to get a sense for just how much more important the strong nuclear force is than the Coulomb force in this total binding energy by expressing the electrostatic potential energy as a fraction of the total binding energy. So let's get started with this Coulomb force. We have the charge magnitudes, we have the separation distance, so we just state Coulomb's law and then plug in. So there's Coulomb's law, it's K Q1 Q2 over R squared. Plug in K, and then each charge is the same and it's equal to the elementary charge, 1.6 times 10 to the negative 19 coulombs. So I'm just going to write that as 1.6 times 10 to the negative 19 squared. And then we divide by the square of the separation distance, which again is 1.68 times 10 to the negative 15 meters. When we run the numbers on this, we get 81.5 newtons. And that might not seem like a huge force, but when it's applied to particles this small, that's enormous. If that was the only force acting on these protons, they would fly apart with immense acceleration. Next, we look at the electrostatic potential energy between the protons. And that's given by K Q1 Q2 over R, so we're not squaring the separation distance in that. And when we run the numbers on this, we get 1.37 times 10 to the negative 13 joules. Now we're asked to convert our answer to electron-volts, which are generally more appropriate when we're talking about the subatomic world. And I'll post a link to the video where this was derived, but the conversion to electron-volts is given by 1 electron-volt for every 1.60 times 10 to the negative 19 joules. When we run the numbers on this, we get 856,000 EV if we keep 3 sig figs. And like most of what we do with nuclear physics, it's best to convert to mega electron volts, so we shift the decimal point 6 times and get 0.856 MeV. So now in part C, we're going to get the total binding energy for this nucleus. And the strategy is very simple here. We just look at the mass of all the ingredients that go into the nucleus. That's 2 protons and 2 neutrons. I have the mass of a free proton here and the mass of a free neutron. And then we compare to the mass of the entire nucleus and we ask ourselves how much mass is missing. And it's the energy equivalent of that mass that tells you the total binding energy for the nucleus. There's a second point that I want to make before we proceed with the calculation. The units are given here as MeV per c squared. Those are our mass units. And once you find that total missing mass, you're going to convert that to an energy by using E equals mc squared. I can see that when I multiply the missing mass in these units by c squared, I get mega electron volts for the energy. And I'll post a link to the video where I first discussed the units of MeV per c squared. So we move forward with getting our missing mass. There's the mass of the ingredients, that's 2 protons and 2 neutrons. Then we subtract the mass of the alpha particle that's formed from those protons and neutrons. And when we run the numbers on this, we get 28.3 MeV per c squared of missing mass. Again, when you want to find the actual energy equivalence of that, you just plug m into E equals mc squared. The c squareds cancel, and I get energy in mega electron volts. So my binding energy is 28.3 MeV. Finally, in part D, we want to take a look at how weak the Coulomb force is compared to the strong nuclear force by just expressing the electrostatic potential energy as a fraction of the total binding energy. So that positive potential energy due to the Coulomb force was 0.856 MeV. But the decrease in potential energy as this nucleus came together, that's the binding energy. That's 28.3 MeV. And when I run the numbers on this, I get about 3%. And this just gives you a qualitative sense for how much stronger the nuclear force is than the Coulomb force. What's going on with the Coulomb force is only accounting for 3% of the energy considerations in this nucleus. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.